Okay, our penultimate talk in this session is Maria Cervetnik and colleagues. Early visual cortex is recruited to act as a comparison circuit between mental representations and visual inputs. Take it away.
Hello. Yes, my name is Maria Cervetnik, and today I'm going to talk to you about the early visual cortex and why it may be recruited for stuff besides perception. Oh no, gotta wake up, y'all. So I'm going to start by saying that we keep mental representations of things we've seen across a variety of tasks and contexts. So for example, this is Robert, and he's walking to his friend's house through a forest. He has a mental representation of the house, but he knows he's in a forest, his friend doesn't live in a tree, so the representation can be stored passively. When Robert finally comes to the town and needs to actually find his friend's house, however, this representation is used to compare to the incoming visual input. And you might be like, this is a visual working memory task. Or in a visual memory general session, this is delayed match to sample. But if you think more broadly, Robert maintained the representation in his long-term memory, then brought it into working memory, and is now using it as a template for visual search. And what is in common throughout all of this is that Robert has seen something, he is not currently seeing it, but he has a representation of it. So for the purposes of this talk, I'm going to call this representation of a thing you've seen but aren't seeing currently a mental template, just so we don't all get confused. And to understand how these mental representations are used to compare them against sensory inputs, we can turn to brain data. For example, we can decode information about visually perceived stimuli from the primary visual cortex, V1. And what about mental content? Well, actually, we can also decode it from V1. And here you can go, Maria, but V1 is the first cortical site for perception, depending on how up-to-date you are with the literature. And we can decode representations that aren't currently perceived. Why? That's actually a really good question. And one way of thinking about this is, well, visual input, of course, comes to us in a visual format. And if you have mental content in a visual format as well, then the V1 would be a very efficient site if you need to perform a high-precision comparison at the earliest possible opportunity. So we hypothesize that V1 acts as a sort of comparison circuit between visual inputs and mental representations. And in order to test this hypothesis, we recruited 15 participants and brought them into an MRI scanner where they performed the following task. At the beginning of each block, they saw two templates. Those are random dot motion stimuli with 100% coherence, so like clouds of dots all moving in the same direction. And then one of the templates is skewed, which means the participant will now have to maintain it for the next 7 minutes. After a delay, the fixation changes color, and then a probe, another random dot motion stimulus appears on the screen. So for this participant, if the fixation turns green, then they have to perform a comparison. They have to say if the probe is clockwise or counterclockwise relative to the template. And throughout the block, they perform 24 such comparisons. The fixation can also change color to red. And then they will again see a comparison probe, but now the only thing they have to do is press the third button. I'm going to call trials like these non-comparisons. There are 24 of them as well, and the order is randomly interleaved of comparisons and non-comparisons. And some people may wonder, so I'm going to say right away, that the template and probe directions are independent, not yoked. I know, right? Very fancy. And so at the end of each block, the participant sees an arrow that they now have to rotate just to report the motion direction of the template they've been maintaining. And they perform 32 blocks with 32 unique templates over 4 scanning sessions. And we have contrasting predictions for the decoding of the sensory input, the probe itself, versus the mental template. First of all, we expect that the sensory input is going to be decodable from V1 whether it is used for comparison or not, whereas the mental template is only going to be decodable from V1 when it is compared against sensory input. Secondly, to further test our hypothesis, we manipulate probe motion coherence. So the probe is either 100% coherent, all the dots moving in the same direction, 50% coherent, so half of the dots moving in the same direction, half doing whatever the hell they want, moving randomly, and then 0% coherent, so no discernible motion at all. And we hypothesized that for the decoding of the probe coherence, of course, should play a big role. If it's 0% coherent, there's no signal to decode, it should not be decodable. Whereas it should be decodable for 50 and 100% coherence. On the other hand, if the comparison is what matters for the representation of the mental template, then when it is used for comparisons, it should be represented no matter what it is being compared against. And so we expect that the decoding will be affected by probe coherence for the sensory input, but not for the mental template. Before I show you all the cool results, did my participants do the task? Well, they remember the template motion direction for 7 minutes pretty well. They also have these 2 tasks that they have to switch between. Either they press clockwise, counterclockwise, or they press the 3rd button. They do this correctly about 90% of the times. And when they are performing a comparison, they also do this with a high accuracy. Besides accuracy, I can also look at their reaction times. And here I'm going to look at it across comparisons, non-comparisons, and 3 levels of coherence. And first, for non-comparisons, this is a super easy task, right? You see something, you press a button, they're very fast. Coherence doesn't matter. Whereas if you look at the comparisons, they're significantly slower, and interestingly, they don't know that the 0 coherence probes are 0 coherence. I lied to them. And so they're still trying, my poor souls, to perform a comparison. This is not a statistically significant difference, but if anything, they're slower in the comparisons for 0 coherence. So altogether, it looks like they are performing this comparison task the way we want them to. So now what about the brain data? To test our model, we collected independent data from a sensory mapping task, where the participants see, again, random.motion stimuli with 100% coherence with different directions. They have 256 trials of those, and the only thing they have to do is detect a slight contrast change, which is super easy. They do it very well. We use this data for 2 purposes. First, to localize visually responsive voxels, the parts that care about our stimuli, and secondly, more importantly, to train an inverted encoding model that we then apply to the data from our main task. So we can use this model and decode sensory input or mental template. And here, in order to orient you a little bit in my trial, this is when the comparison probe is on the screen, and this or this when the next comparison probe might come on the screen. So, for the sensory input, it's highly decodable both when it is compared and when it is not compared. Just perception is what matters. For the mental template, as you might guess, the picture is very different. Mental template is only decodable from the primary visual cortex when it is used for comparisons, but not otherwise. And since we have these very short intervals between probes, we also estimated the hemodynamic response function shape and fit it to each voxel in each trial to estimate bold amplitude in response to each probe. So this way, we kind of harness data from multiple time points, and then we get one decoding prediction per trial. And if we look at these data, the results are consistent with the over time decoding. Namely, sensory input is represented independently of the task, whereas mental content is only represented when it is used for comparisons. We can also look at our data for different levels of the probe coherence, and here I'm splitting them by comparisons and non-comparisons. So when I look at the decoding of the sensory input, it is not decodable for 0 coherence, and it is significantly decodable for 50 and 100% coherence, and that's true for comparisons and non-comparisons alike. For the mental template, on the other hand, if it's being used for comparison, it's always decodable, and if it is not being used for comparisons, it's never decodable. So, to sum up, the sensory input decoding depends on probe coherence, whereas the mental template decoding depends on comparison, but not probe coherence. And so, to kind of come back to my big question, does V1 act as a comparison circuit, where I don't think we have the answer to that? Do we have an answer, which is that mental representations seem to recruit V1 when they are compared against visual input, and specifically when they are compared against visual input, which is of course in line with this idea of V1 as a comparison circuit. And if you take a little bit of a step back, I think this also highlights something very important about how we should be thinking about this thing at large, which is that to understand how information is represented to the brain, we need to consider how this information is used. It's not universal. I'd like to thank my lab, especially the people on the left, Giuliano Giugiani, there's Simone Verenlekerci, who helped me with data collection, and Rasmus Zinn was amazing with data pre-processing. If you're interested in more work from the Rademacher lab, you can also go to my colleagues' talks and posters. They're all on Tuesday at 2:45. But if you're very organized, you'll make it. Come to me for advice. And then finally, I don't know what's the cool way to say this, but I'm finishing up my PhD, and I will be on the postdoc market soon. So if that's something that excites you, find me at VSS or send me an email. Thank you very much for your attention.
Thank you so much. This is very cool work. This made me think a lot because sensory recruitment is an interesting idea. And one of the earliest pieces of evidence that we used to sort of support the idea of sensory recruitment is that there are reciprocal interactions between memory and perception where they produce these biases that we see, right? And what's interesting is that you often get these reciprocal biases even in cases where there's no need for any sort of explicit comparison between memory and perception. So if you just tell somebody, ignore this thing that I'm going to show you at the center of the screen, that thing that they perceive still seems to sometimes change how they remember something that they're holding in mind. So if comparisons are the currency of sensory recruitment, does that mean biases aren't fully explained by sensory recruitment, or does it mean that comparisons sometimes happen even when they're not part of our explicit demand set?
Oh, that's a great question. I will need to think about it a little bit more, but I would say I think the stuff you're talking about is very applicable for a typical visual work in memory task, right, where you've just seen a thing, you passively remember it, and then you report it. So this short delay right afterwards is where the stuff you're talking about appears. Whereas this is broader, right? My participants are remembering stuff for 7 minutes. I don't think, like, we see that they're not actively maintaining it the whole time, so the process is different, just at the base level.
That's a really wonderful talk. How about other brain regions?
So we looked so far. No, that's super fair, right? I'm focusing on V1 here because that's what my hypothesis is about. We also looked at V1 through V3 so far, and the results are strongest in V1, but they seem to be rather in line with this in other early visual regions as well. We also, there's a question I want people to ask, which is about regions outside of the visual cortex, right? Where does it go when it's not here? And so we also want to look at some of the stuff that Thomas has looked at, and also the hippocampus. Yeah.
Hi, thanks, great talk. So my question's a little bit broader.
Wonderful.
Just because we can decode something from the activity of V1 doesn't necessarily mean the V1 is using that information to achieve its purpose. I can imagine I record a spike. I think that has some effect, but that spike, because of the connectivity of that neuron, could have some other effects. So could you speak speculatively about how you think we're to interpret what your findings are in the context of what V1 is doing versus what we can extract from what V1 is doing?
This is a super, super good question. I think Thomas already said today that fMRI were sort of limited to correlational conclusions in a way. So here we have not done any brain behavioral analysis just because with the design it's tricky, but there is evidence like that for V1 decoding, so that's promising in a way. But of course, yeah, it could all be an epiphenomenal, but then it's very logical for it to be epiphenomenal. It's too logical for it to be epiphenomenal is what I would say, yeah.
Frank Tong here. Just
Yes.
really enjoyed your talk and Thomas's earlier, and just to say it's really gratifying from decoding my own V1 working memory activity back in 2008 or so, and to see that my brain is replicable. So thanks, good work.
Thank you. You're welcome, and thank you. Yeah. Okay.